Good morning, good afternoon, good evening. I'm about to start the lecture. This is Dr. Ost, of course, History 112. I'm about to start the lecture on the Scientific Revolution, which I believe most of you wrote down. The time period for that is 1543 to 1687, Scientific Revolution in Europe. However, we're going to back up a little bit. Often to understand what's going on, you need to go back a little bit in history. Okay, what European people believed, now when I say European people, educated people are 5, maybe 10% of the European population. Most people are illiterate. Most people are day laborers, they're farmers. Even businessmen might not know how to read, except for, they know some basic math. So when we talk about what people knew, what they understood, what they read, we're really talking about the upper 5 or 10% of the European population. This would be clergy. People in the Catholic Church obviously were literate. It would be a small handful of scholars, maybe noblemen who sent their sons off to university, and then a few people in the royal family. Certainly there were a lot of kings who basically signed their name with an X and somebody else did their paperwork for them. But anyhow, so when we say, let's back up a little bit, what did people know? We're talking about what did the few educated, literate people think? Because most people don't consider these issues. They don't read, they don't write. The average farmer does not sit around wondering whether there's going to be a scientific revolution in his lifetime. But let's back up. Let's go back to about 1300. So let's talk about what's going on very quickly in Europe between 1300 and 1500. And there's a lot of things going on. There's a lot of changes that will lead to and help support the scientific revolution. One of the things that's happening is the Renaissance. And most of us think of the Renaissance, which of course is spreading across Europe, as all about art and architecture. But the Renaissance was also a lot about math. There's a lot of math involved in architecture, and there's actually a lot of math involved in the perspectives that are used in painting. So there's some new mathematics developing. There's also the Protestant Reformation. The Protestant Reformation begins around 1519, and we're not going to go into all of that. There's a lot of warfare, there's a lot of conflict. Eventually there's a settlement, and the princes in every region of Europe get to decide whether their people will become Catholic or Lutheran or Church of England, whatever. The issue, though, that's important to us, what you want to write down, obviously Renaissance mathematics, that's what you should have written down. When it comes to the Protestant Reformation, which basically changed Europe between 1519 and let's say 1600, is that Protestants emphasized literacy. Protestants wanted everyone to be able to read the Bible for themselves. So they emphasized education. They emphasized teaching people how to read. Now, did all of Europe immediately become literate? Of course not. And did everybody run out and buy a bunch of books? Well, no, because there weren't a bunch of books to buy. But slowly but surely, especially people who lived in Protestant regions, which is why most of the scientific revolution took place in those regions, those were areas where there was a huge emphasis within the churches on teaching people how to read. And if you teach people how to read the Bible, they can also read other stuff, like scientific stuff. They can become educated. And then a third thing that we need to keep in mind is the printing press. 1450, 1453, right in there, a movable type Gutenberg who you may be familiar with, a German man invented or designed a movable type printing press. Now, there were other parts of the world that had printing presses, but the movable type thing is really important. Um, in a nutshell, movable type means that you can very quickly and relatively inexpensively produce books or pamphlets or essays or leaflets or whatever. Prior to that, every single book was copied by hand by a monk in the Catholic Church. It took forever, and books were extraordinarily expensive. So the invention of the printing press right around 1450 means that now books are more available, they're less expensive, and they middle class people can now afford books. And really, more than books, what was printed were leaflets, little pamphlets. You know, you write a 30-page thing on some aspect of science, and you go to the print shop, and you have 100 copies made. And that was now something that you know, middle class and above people could afford to do. So in other words, the Protestant Reformation especially, and the printing press meant that all of a sudden there was more knowledge, more information, more stuff to read, and the European population was improving in terms of its educational future. The last thing I want to mention before we get into the actual revolution is navigation and shipbuilding. This is a time period when, by the time we get to about 1500, most kings and queens are desperate to acquire territory and establish colonies. And so, of course, kings are putting some money and some effort into new navigation technologies, new tools, new instruments, and they're also investing money in improving the quality of shipbuilding, because all of that, good navigation tools and good shipbuilding tools, have everything to do with the fact that you want to be one of the first kings to get to a new part of the world and establish a colony. So, as you probably can imagine, shipbuilding, a lot like architecture, requires a real strong understanding of math, in particular geometry. Excuse me. In terms of navigation, star charts, the navigational tools used by men on ships are going to contribute to an understanding of astronomy, and that's right around the corner. So those four things, the Renaissance, the Reformation, the movable type printing press, and the fact that kings are investing money in both navigation and shipbuilding, all of those things kind of get you prepared for the coming scientific revolution. So you want to skip a line, skip a space, and beginning in 1543, this is the date that most people use for the actual revolution. And there are probably across Europe anywhere from 100 to 200 well-educated men that we would call scientists or researchers. But we can't possibly study all of them. So I want to give you 6 or 7 major names, tell you what they discovered, talk about it a little bit, and then show you how they connect kind of in a way. They build, once again, history tends to build upon itself. So we're going to start with a man named Copernicus. You've skipped a line. You've written Revolution, 1543. Copernicus, Copernicus. I'll do it again. Copernicus, Copernicus. Copernicus was a Polish clergyman. He was a member of the Catholic Church, but some of the clergymen were very, very well. Now, the basic priests were not, but if you got to be a bishop or an archbishop, you could be quite wealthy. In fact, you might be from a noble family who had a lot of money even before you became a clergyman. And so he was both a clergyman, had a lot of money, nice house, servants, and he liked astronomy. So Polish clergyman, astronomer. Now, when Copernicus was a young man, most of the ideas about astronomy or the heavens were very, very archaic. They dated back actually to the Greek philosophers, before the time of Christ. And everything was considered mystical. Everything in the heavens were the place where the spirits lived. Well, Jesus comes by AD 300, 400. The Catholic Church is well established, and the Catholic Church actually borrowed some of those ideas. The Catholic Church was not interested in looking up at the sky and going, oh, astronomy, let's do research. They looked up at the stars in the sky and thought, oh, God's glorious heavens. The stars are speaking to us about God. They thought the stars were very close to Earth. They thought heaven, the clouds, God, was a place that was very close to them. And so for them, the sky, the universe, was something that was spiritual. It was mystical, magical, spiritual. They didn't think in terms of science, or like, well, what's up there and what is it made of and where are the planets. They didn't think in terms of, things like we do, like planets and stars. They was just like, the sky's beautiful, God created the universe, we get to enjoy it, here it is. So there were a lot of backwards, erroneous, and mistaken ideas that had begun with the ancient Greeks, continued down through the centuries, and basically the Catholic Church bought into them because they weren't really interested. And one of the things the Catholic Church bought into was the idea that God had created everything out of perfect circles. So stars were perfect circles, planets were perfect circles, the orbit of the moon around the earth was a perfect circle, and so on and so forth. Now, Earth itself, which was a fallen world, the devil had come, the earth was not perfect, but everything else was perfect. And so if you were an astronomer and you're a member of the Catholic Church, everything you did, you're studying, you're measuring, you're looking up at the sky through a telescope, everything had to come back and fit into this perfect circular theory. That means that most of all research and most all astronomy was completely worthless and wrong. But they did not know that at the time. So a little bit about Copernicus. What the church had also done, I should have mentioned this, the Catholic Church had for centuries said and believed and taught everybody the earth is the center of the universe. They actually thought that our solar system was the universe. They didn't realize there was another universe beyond. The earth is the center. Well, as long as you try to think the earth is the center of the universe, then when you try to measure and figure out where the planets are and understand the universe, it doesn't work. So Copernicus, after much study, much watching the stars at night, thinking about the moon, the earth, the planets, he came up with two major things. He said, actually, the universe is immensely huge. It's not small. They kind of felt like, well, if we stood on a mountaintop and we reached up, we could touch the stars. And of course, the stars are, millions of light years away, not just years, light years. And so Copernicus was able to figure out, or at least he thought, and he was right, that the universe was actually huge, that it was enormous, and that our planet and the other little planets that circle around us are a very small part of the whole. But of course, the Catholic Church didn't believe that. He also said, this is what they got most upset about, he said, the sun is the center of our solar system, and that's a small part of this huge universe. Well, the Catholic Church said, no, the earth is the center. God created the earth, he created man, we are the center. We've always been the center. And of course, Copernicus says, well, no, and he wrote a whole book, full of diagrams and information and his reasoning, his scientific reasoning. Here's the deal. This is not too far from the time of what we call the, oh shoot, now I've forgotten the word. The time period when the Catholic Church tortured people and put them to death, and it'll come to me in a second. Anyhow, the Catholic Church had prisons. They had their own army. And if you didn't believe the way they believed, you would probably be arrested, and you might be tortured, and you might be murdered. So Copernicus writes this book. He says, look, I don't understand everything, but this I think is wrong, and this is wrong. Here's what I think is right. He waited to publish his book, 1543. He was on his deathbed. He wanted to make sure that in case he was wrong, or in case the Catholic Church thought he was wrong and came after him, that he would be long gone and dead. So he published his in 1543. The next individual we need to talk about is a man named Brahe. B-R-A-H-E. So skip a line. B-R-A-H-E. Brahe was Danish. He was not a clergyman, but he was a nobleman and he had money. And Danish people come from Denmark, and there's a piece of Denmark that kind of extends out into the sea, into the North Sea. And it was a fabulous place to build a castle and a tower and an observatory. And so this is what he did. He was fascinated by the stars, by the sky. He had servants, he had money. He built a tower. Now, Brahe is not much of a mathematician, and many astronomers are. They have to be. But what Brahe was an incredible observer. You should write that down. Brahe was an observer. And he built this tower, and they're sitting out on this little spit of land out in the middle of nowhere. It's dark. What's the best time or the best way to see the stars at night? When it's completely dark, when there's no city nearby, and there's no lights and there's no fires. So Brahe and his servants, they would study the night sky. They did this for years and years and years. And every night, when there was no clouds obviously, every night they would basically, let's call it a star chart because that's what it was. They had these big sheets of paper, kind of cover a table, and they would carefully document every star they saw, every star cluster, every time a planet arced through the sky at night. They made a record of it. They knew where the North Star was because that was an easy one to recognize, excuse me. And every night, for years, there were thousands of these star charts. And Brahe was just an observer, and he accumulated information. He dies, but one of his helpers, one of his assistants, is a man named Kepler. And I would imagine if you aren't familiar with Copernicus and Brahe, you might be familiar from a science class with Kepler. Kepler was his assistant, not a servant, an educated man, very well trained, a terrific mathematician. So next to Kepler, educated, terrific mathematician, very important. And he inherited, or he took, I'm not really sure which, that big huge pile of star charts, which was basically 20 years worth, several nights a week for 20 years. He took the entire star chart stuff and he began working with it and trying to understand it and trying to convert. What Kepler wants to do is he wants to convert a picture of data, a picture of the heavens, a picture that basically, a graph or a diagram of all the stars, and somehow convert all those pictures into mathematical formulas, into a mathematical formula that would make sense. So let me explain why this is important. Kepler's got, let's say he's got 1,000 sheets of paper. I don't know exactly how many there were. He can study them, but to communicate with anybody else, with any other scientist, he's going to have to either take the 1,000 sheets of paper to them or have them come to his observatory or his office and sit down and look over them. That's like insane. That's ridiculous. It's complicated, it's difficult, can't be done. If he could come up with some simple mathematical, algebraic perhaps, formulas to describe what's going on these star charts. Why are the stars rotating this way? Why do certain comets appear at certain times? Why do certain constellations appear and then move across the sky? See, there are reasons for all of that. We can all take, you may have done this in a class, we can take most of the phenomena, the things that happen in our solar system, and we can explain them using mathematics. Now that's not what we all want to do. Some of us like to say, okay, the stars, we describe the stars in the sky in poetry, or we describe the stars in the sky by taking photographs. But you can describe what's going on in the sky by using mathematics, and that's Kepler's strong point. So he works and works and works for years with all this material, and he writes a book. They all write a book, and in his book, it's a long book, it's very complicated, it's called The 3 Laws of Planetary Motion. So Kepler's book is The 3 Laws of Planetary Motion. And it's very complicated and it's full of math. And you'll be happy to know that we're not going to talk about any of the math because I don't understand it. I don't expect you to understand it. So in English words, here are 3 very important things that he proved mathematically. 3 very important. And by the way, Kepler is in Germany, where Protestant rulers are in charge. So he's not really in danger with the Catholic Church. You don't have to write that down, I just thought I'd mention it to you. 3 laws of planetary motion. I'm going to pause momentarily. You might want to take a break, and then we'll continue the lecture. Okay, Kepler's book. Number 1, he proved that the orbits of all the planets are elliptical, kind of like egg-shaped. The orbits of all the planets are elliptical. Why is that important? Because the Catholic Church said they were circular. And so the Catholic Church made everybody afraid. And so all scientists were saying, yes, they're circular, even though that's not true, and the math didn't prove it out. So how can you have a science if it's based on wrong information from day one? So Kepler is basically proving what's correct. All planets move through space in an ellipsis. They're elliptical. And there's mathematics for that, by the way. It's crazy to me, but whatever. Number 2. As the planets move through space, their speed changes. As the planets move through space, they go faster, they go slower. They go faster, they go slower. That's important to know. For the past 900 years, everybody thought, well, all planets move in a circle, perfect circle, and they go exactly at the same speed all the time. They don't. Okay, which leads us to number 3, which kind of explains why they don't. Number 3, the time that it takes for a planet to orbit the sun is mathematically related to its distance from the sun. Right now, let's just write this down, and then we'll talk about what it means. Number 3, the time required for a planet to orbit around the sun is mathematically related to its distance from the sun. That's a complicated one. I'll do it one more time. The time required for a planet to orbit the sun, our sun, we're talking about our solar system, is mathematically related to its distance from the sun. Now, 2 things. Kepler does not understand gravity. He's not trying to explain or describe gravity. That's not going to happen until Newton, and that's in 1687. But what he's done is he's put together for the first time, think about it, when a planet is orbiting in an ellipse around the sun, when it's closer to the sun, on the long side of the ellipse, it's going to feel the gravitational pull of the sun. It's going to go much faster. When it gets out of the far end, this end or this end, either one, of the big ellipse, it's very far from the sun, and the gravitational pull is much weaker, and so it goes slower. So if you were to watch them, if you were to watch in fast sped up time, real fast, slow, real fast, slow, the way that a planet travels and the orbit that it takes and the time that it takes, you can figure it out. If you know the distance from the sun and you can measure some points in the orbit, you can figure out what's going on and how fast it's orbiting. And you can begin to predict. If you have part of that information, you can predict where you're going to see the next planet, or you can predict how fast it's going to go. These are all very useful things in astronomy. So he publishes his book. There's no big deal about it. And I want to talk next, skip a line, skip a space, start a new paragraph. Somebody that I think you're probably all familiar with, Galileo. Galileo, Galileo. He's also really good at math. In fact, he works at a university. He's a professor of mathematics. Galileo. And what you probably know about Galileo is that in 1609, He built a very high quality telescope. He built a very, now there were telescopes already being built in Europe. They were being built by the Dutch, but he's one of the first people to build a really high quality one and use it to study the stars. So 1609, I won't give you very many dates, but this one's kind of important. 1609, he builds a very high quality telescope. And he's a mathematician, but he's also, with his telescope, he's an observer, a lot like Brahe was. And by now, of course, he's read the book by Kepler. He kind of knows that there's some new ideas out there, and there's some questions about the heavens, and that maybe everything the Catholic Church is, and he is Catholic, by the way, so we're going to run into some problems here. But using this telescope, three major things that he observed and he wrote about. There's lots more. Again, he wrote a book like everybody else. He observed that the moon's surface, looked a lot like Earth. In other words, it was rough and bumpy, had mountains and chains, and it looks like valleys where rivers used to flow. The moon's surface was very similar to Earth. It was rough and imperfect. That's the word you want to write down. The moon's surface was rough and imperfect. And why is that a problem? Because the Catholic Church said everything in the heavens was perfect and circular and divine and celestial. And so the Catholic Church is going to be upset with him and say, no, the moon is this glowing, beautiful orb of light and spirit and power. It has to do with God. It is nothing like the planet that we live on, or the earth that we live on. So that's where we're going with this. Number two, he observed, I'm sure that you all have, if you haven't seen them, you've read about them, sunspots. Every so often, there is a disturbance on the surface of the sun, and the gases change and do who knows what. I don't know how to explain it. And they're visible darker spots on the surface of the sun. You can see them sometimes with the naked eye, sometimes with a telescope. He observed some spots on the sun's surface, and he observed that they kind of moved around and they would disappear for a while and they would come back. Again, why is that a problem? Because according to the Catholic Church, everything outside of Earth, everything else was created by God, and it's got to be perfect, eternal, unchangeable. That's one of the meanings of eternal. It's got to be perfect. It can't have any blemishes or flaws. And sunspots were seen as, why is he making up this crap trying to make us uncomfortable about God's perfect creation? So the Catholic Church is not going to like that for sure. And number three, he spent a lot of time observing Jupiter. Jupiter has a whole series of small planets, or moons, you might call them, that are circling it. Again, that's a problem for the Catholic Church. There isn't supposed to be any other Earth. There isn't supposed to be any other moon. That just doesn't work for them. They're just supposed to be these major planets, and everything's supposed to be circular and perfect and divine, the way God created it. So seeing all of these things was in a way seen as challenging God. And certainly it was seen as challenging the teachings of the Catholic Church. And remember, the Catholic Church has one leader, the Pope. But they are like the Church of Europe. They're the Church of 17 different nations by now. So, as you might know, Galileo was arrested because he does publish his work. He talks about it. He's arrested. He's put on trial. Um, he's made to basically recant. That word is recant. He is made to recant his work, which means to say, I was wrong, I was mistaken, I was confused, the devil told me this. There's lots of different ways you can recant. But basically you say, and sometimes even when you recant, the Catholic Church might still put you to death. That was called the Inquisition. What I was trying to think of earlier, the time of the great time of turmoil and torture and death, was called the Inquisition. And there were several Inquisitions under, bigger and smaller, under the Catholic Church. So if you were Catholic, you needed to be careful what you said, what you believed, and what you wrote. Okay, he's arrested, he's put on trial, he's under penalty, he's put in a dungeon, under penalty of possibly losing his life, if not just being imprisoned. He does eventually recant and says, I was mistaken, I was confused, I realized this was inappropriate, and he's put under house arrest for the rest of his life. They don't kill him, they don't keep him in prison, but he's put under house arrest, and he's not allowed to leave his home. He's not allowed to have any contact with other scientists or other educated men. However, he has a daughter who he has educated, and she's quite smart, quite well, and they continue to do research privately in the home, and she's allowed to leave the home to go basically buy groceries and things like that. So some of what he's doing, what he's thinking, what he's believing, she is able to get it out to other people. But everybody keeps it very quiet because they don't want him to get in trouble. So that's Galileo. And how are we doing for time? We're doing fine. Okay. The last person, before we get to Newton, there's always Newton. Excuse me. And by the way, don't forget, if you get exhausted, if you get tired, if you need a 2-minute break, pet the cat, rub the cat, pet the dog, get a drink. Just don't go wandering off and forget to come back, because you need these notes, and you need to be accumulating these notes, so when we get to the midterm, nobody's in a crisis. You're not like hysterical, like, oh my God, what am I going to study? How am I going to study? You can't. There's no way to study all this material the week before the exam. It just physically can't be done. And you'll have other classes. If you need to take a break, pause the video and go do something for 2 or 3 minutes. Listen to some music, do some artwork, pet your animals. I don't know. Go outside and sweat, whatever. When it's winter, I'll say go outside and freeze. Okay, it'll be different. But let's go on with Descartes. D-E-S-C-A-R-T-E-S. D-E-S-C-A-R-T-E-S. Now, I'm not giving you the excuse me. I'm not giving you the dates of these individuals, but they are in chronological order. So you need to take your notes that way. And if you, I'm not saying you will have one, but if you were to have an essay to write on something like this, it's important that you have the individuals in the right order, chronologically. Because otherwise, what they discovered and what they learned from each other doesn't make any sense. So you need to have them written down chronologically. And by now, we're up to about 1600. We're real close to the turn of the century. But you don't need to write that down. Descartes is also, surprise, surprise, a great mathematician. As long as we're dealing with astronomy and measurements and speed and light, there's going to be a lot of math involved. I mean, that's just the way it is. And actually, most scientists in most fields usually are pretty good at math. Um, if we go back to what I said earlier, which is still true, there are lots of ways to understand the world that we live in. You know, we can look at things artistically, through literature, humanistically, in terms of art and beauty. Lots of ways that we can look at the world, but to understand it and like take it apart and know how the world works, often it's going to require mathematics. So, anyhow, great mathematician. One of the most important things about Descartes, I keep saying mathematics, and I mostly mean algebra and calculus. The kind of person who uses geometry that's very different from the kind of person who does algebra or calculus. People who focus on geometry, I love geometry. I was good at geometry, and I almost died when I had to take algebra because they're very different. Geometry is about spaces and shapes and angles and straight lines and curved lines, and geometry helps you paint. Geometry helps you build a building or a church, or architects have to know a lot about geometry, and that's one kind of mathematics. It does certain kinds of tasks. And then there's algebra and calculus, which is more about equations. And up until the time of Descartes, you either did geometry, and there was a whole little group of mathematicians who were geometers, and there was a whole group of mathematicians who focused on things like algebra and calculus. These two sets of mathematicians or scientists did not talk to each other. Their mathematics were too different, and there was no way for them to connect. So if you studied something using geometry, then you really never had anything to do with people who studied things using algebra. It was a different method. Descartes, brilliant man, he invents something called analytical geometry. Analytical geometry. Analytical geometry. Sometimes you might put this in parentheses. Sometimes it's called coordinate geometry. Just write G for geometry. What he did, and we'll talk about this just a little bit, because I don't need you to be a mathematician. I'm certainly not. He created a mathematical language so those two different disciplines could talk to each other. He created a mathematical discipline, analytical geometry, coordinate geometry, so they could talk to each other. Not so they could talk to, so they could do mathematical work together. That's what I mean when I say talk to each other. I don't mean they went for coffee, but I mean you could do a bunch of geometric figures describing, for example, okay, here we go. You could use geometry to describe the arc of a planet through the heavens. Or you could, use geometry to describe where a cluster of stars is. After the invention of analytical geometry, you can convert that geometric thing into an equation. You can write a page full of equations that the right person with the right skill mathematically can say, oh, well, what that means is, and he could go back and say, well, that means that the moon goes this way and Mars goes that way. You can draw a picture of the universe, or you can convert that picture of shapes and movements and curves and lines, you can convert that to a set of equations. And with the right, if you're a good mathematician, you can take a page full of equations and recreate the picture, the map of the sky, of the solar system. I don't know if you're excited. You should be. This is incredible. This was an incredible, I mean, we take it for granted now, but it was unbelievable that now there was a mathematical language, analytical or coordinate geometry, that allowed all kinds of different people to understand the same solar system events and phenomena, and they could describe it to each other. So that's the, and by the way, analytical or coordinate geometry, you may or may not know what that is, and you may know a lot more about it than I do actually, but some of you may not know what it is, and you have come across this. I'm almost positive you've come across this in a class, even if you don't know that you've done this. For example, have you ever had to draw like an XY axis, X, Y, and then you're given a series of points and you have to graph them like it's graph paper? It's got all these lines. But that really looks horrible when I do that. Sorry. That's coordinate geometry. So, and by the way, you can take an equation, convert it to coordinate geometry, dot, 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 put your little series of points, and you can recreate a curve in space. You can recreate the orbit of a planet in space by using these diagrams. And you've all done an XY axis thing. I know you have. I mean, I did those like in 7th, 8th grade. So yeah, this is just amazing because it's going to allow people in many different kinds of fields to interact with each other. A couple of things real quick about Descartes. He developed a 4-step process for basically doing science. He developed a 4-step process. And this is going to sound probably very primitive to you, but up until this time, let's not forget, and I haven't told you this, but I should have, a lot of science in this time period was real close to being magic or imagination or hocus pocus. You know, people didn't keep good records. They didn't really, if somebody was sick, you gave them 7 different herbs, and maybe they lived, maybe they died. Nobody knew which one killed them. Or, people didn't do experiments the way we think of them now. They just tried things, and maybe it worked, maybe it didn't. There was still a great belief in the fact that angels and demons did things on earth all the time. And so, there really was no need to be scientific. There was no need either the devil made it happen or God sent an angel. And so you don't really need science. And there was still strong belief in witches, and witchcraft, and spells. There was a lot of heathen, kind of barbaric stuff mixed in with Catholicism. So, a lot of people who were, quote, thought they were doing some sort of science or research were really playing at magic. They were playing at guessing. So this 4-step thing is really kind of important. So if you want to understand something in the solar system, if you want to understand the universe, Descartes said, number 1, never believe anything is true Investigate for yourself. So just because somebody says so, or just because it's in a book and somebody wrote it down, never believe that something is true until you investigate it for yourself. That's number one. Number two, never try to answer a complicated question or a complicated problem. Never try to answer a complicated problem. Divide every problem into many small parts and then solve them individually. Never try to solve any big complicated problem. Divide the problem into many small parts and then work to solve each one of them individually. Number three, as you're doing this research, as you're doing experiments, start with very simple concepts and then go to more complicated. Always begin with what's simple, like, what is this thing hot or is it cold? You don't need to worry about, did this thing come from the sky or a mountain? Is it hot or cold? Is it heavy or light? Is it hard or soft? Always start with simple, basic things. Learn as much as you can about something, and then go on to more complicated ideas. So simple and then complicated. Number four, write down everything you're doing. Write down every step of your research. Write down every step of your experiment, of your process. And then he says, go over it, go over it, go over it. Check your problems, check your math, look for your mistakes. Get somebody else to go over it. Have them look for your mistakes. And always make sure that you verified your conclusions. If you run through an experiment one time and you have an answer, he said, you don't have an answer. He says you run through it 6 more times. If it doesn't come out the same way every time, you've got a problem. Figure it out. So, in many ways, Descartes is the beginning of what we call the modern scientific method that we all, hopefully, that we all use. The last scientist that we're going to talk about, and we're probably going to go to about 65 minutes. We've got about 12 more minutes left. The last scientist that we're going to talk about is Isaac Newton. He's English. He also, if I'm not mistaken, he was clergy. Isaac Newton. And basically, what Isaac Newton does is he brings together the research, the results of all these people that we've talked to. And so he basically brings together before Newton, there were 2 types of science. Physical, experimental science. You crack the rock open, you look at it, you investigate it, you put the fluids in the test tube, you put heat underneath it, and you watch for what happens. That's experimental. And sometimes you don't use any math with that. You do various kinds of experimental things, and you can find a lot of stuff out. You can learn a lot. Or there were scientists who were what we call theoretical mathematical. You should write that down, of course, obviously. There was the experimental, and then there is theoretical mathematical. So let's look at it this way. Let me say it one more time. Theoretical mathematical. If you're studying the stars, you're never going to get to touch them, weigh them, measure them, see if they're hot or cold. You know, you have to theoretically, what do you think a star is? Now you can use math to say, okay, the star is so many million miles away, it's moving so many million miles across the universe. But when you think about it, you can't do science on the stars or comets or planets the way, or even things at the bottom of the ocean, the way you can, now you can't now because we have submarines, but whatever. The way you can measure others, you can study other stuff. He basically pulls these together, and he goes back and looks at Copernicus, Brahe, Kepler, Galileo, Descartes, and he pulls knowledge, processes, information from all these different scientists and uses it all together to try and understand our solar system. To try and understand our solar system. And he produces his book. Now, by the way, Newton did a lot of different stuff. He studied all kinds of stuff. Some of it was a bit weird. That's okay. But the book that we're concerned with, that brings us to, quote, the end of the scientific revolution, 1687, is called The Mathematical Principles of Natural Philosophy. The Mathematical Principles of Natural Philosophy. And natural philosophy is basically the word they used. Today we call that science. But philosophy is love of wisdom, love of knowledge. So it was the philosophy that where you study and you learn about nature. So natural philosophy basically meant people who practice the studying, the education, the learning about nature. And again, today we would call that science. Mathematical Principles of Natural Philosophy. In terms of our solar system, and the sun, and the planets, and the moons, he said all of these things can be measured, they can be timed, they all have to do with ellipses. And he came up with, he didn't fully understand it himself, we don't still fully understand it, but he came up with, and he was able to write about the influence of gravity, or gravitational pull, that one body, one physical body, comet, earth, whatever, or star, is going to have a certain gravitational pull or influence on other items near them in space. So he writes about that, which of course nobody at the time understands. Kind of seems like magical hodgepodge to most people at the time, but he writes about that. And he's very convinced that all matter, everything physical, not spiritual stuff, everything physical, if there's a moon here and a planet here, that they have a gravitational effect on each other. Even though we can't see it, even though we don't fully understand it, they have a connection. And that changes how planets move, how fast they go, where they go, so on and so forth. It's hard to explain because it was so incredibly intellectual and mathematical. It's hard to actually explain in a way that would make sense to us what exactly is in Newton's book. And it's a huge, long, exhaustive, detailed, very mathematical book. I think what's more useful for you and me is to understand what his work accomplished. How did Newton's work influence the world that we live in? So very quickly, and I'm going to give you a list of things that if you were to write an essay on this, I would want you, this is what I want you to know. Not so much about, yes, I want you to know that he combined experimental and theoretical mathematics, but using Newton's work in the next 100 years, excuse me, I'm losing my voice. I'm not sick. I've just talked for a long time today. I'm just losing my voice. It'll be back in time for the next lecture. Don't worry. Newton's mathematical work from this book was used for the next 100 years easily by all kinds of other scientists, and they used Newton's math to predict tides. That seems like no big deal. If you're navigating, if you're bringing ships in and out of a harbor, tides are really important. So his math is used to predict tides. It's also used in all kinds of other navigation to get ships safely across oceans. His mathematics eventually is going to help people learn how to determine longitude and latitude. So longitude and latitude, if you don't remember, are the, quote, imaginary lines on a globe. So we're talking about cartography. Cartography is the study of maps, and maps are the best representation we have of our real planet or some other planet. There are maps of the moon's surface, for example, although I don't know how you would use them exactly. Newton developed a particular kind of calculus. His calculus was able to, without the XY thing, you don't need that anymore. His calculus could describe curves in space. It could describe what are called trajectories. Like when you shoot something out of a cannon, you shoot a cannonball, that's called its trajectory. You could actually describe that. Or a bow and arrow, if you shoot an arrow, if you know the angle that it's being shot at, and you know the strength of the man's pull or the woman's pull on the bow and arrow, you can predict how far is the arrow going to go and what kind of curve is it going to take before it lands. So curves are also used in shipbuilding. Curves are used in architecture, in building bridges. So there are hundreds and hundreds of ways that we still use basically things that Newton discovered and wrote about today in the regular world that we all live in. So calculus, improvements in curves, architectures. They use this not only to measure cannons and cannonballs, but to improve weapons of war, to improve artillery, to improve the various weapons that you use when you're attacking an enemy. Naval ordnance. One of the reasons this is so important is before Newton, Europe did not actually have any kind of military advantage over the rest of the world. There was no reason to believe, if we could go back to 1687, there was no reason to believe that the European nations would one day rule the world. You know, you could have looked at the Chinese civilization or maybe the Indian. There was nothing much about Europe that said, yeah, they're going to take over the world. They're going to rule the high seas. They're going to build all these colonies. They're going to defeat all these countries. That's a combination of extraordinarily good shipbuilding, weapons building, and navigation. And all three of those things benefited enormously from Isaac Newton's work. I don't think that that's what he expected. I don't think that's what he anticipated. He had other weird things he was interested in, but nevertheless, his work, his mathematics, used by other scientists and designers, gave Europe an incredible military advantage over the rest of the world. And eventually it's going to give, because America tends to inherit and borrow from, and America was settled by people primarily from Europe. America is eventually going to have this enormous military and industrial advantage over the rest of the world. One last thing that I want to mention. Believe it or not, and we are eventually going to talk about the Industrial Revolution. And when we do, we're going to talk about the steam engine. And the steam engine was essential to coal mines, to the Industrial Revolution, to all kinds of things that we're going to talk about. The mathematics that were developed by Newton are used to improve the steam engine. So we're done. I know this was a little bit long, but not really. Because a regular in our classroom, we'd have to go for 75 minutes. So we've only gone for 66, 67 minutes. You're getting a few minutes extra. Our next lecture is going to be on the, I think I've left one out. We'll figure it out. It's either going to be on the Enlightenment or the French Revolution, but don't worry because I'll be with you. You'll be listening to the video, and check your syllabus. Make sure that you know what's coming up. If it's time, you need to start working on the first homework assignment. You can always work on things early. And the assignment is like 4 different chapters, and I've given you the questions for that. Again, that is not something you can do in like a day or 2 days. That's an assignment to work on in the evenings, on the weekends, over about a 2.5 week period. So pay attention to the due deadlines, due dates. Make sure you established a 112, History 112 folder on your whatever computer you use, and keep dumping stuff in it. If you've done assignments, if you've taken your lecture, you've seen the lectures and you've taken notes, put a copy of the notes in there for yourself. And if you're not using a computer, then you should have a physical paper folder that says History 112 and keep putting everything in there, because you're going to need to have all that together to get through this course successfully. Have a good weekend, and I look forward to seeing you again. Stay safe. Be careful. COVID is a serious disease, and you don't want to catch it and or spread it. And have a good weekend, and stay on top of things. Email me if you need to. Read your syllabus. Read your syllabus. Read your syllabus. Thank you. See you later. Bye-bye.